In this video, we'll talk about why caching works so well, and that's because of the principle of locality and the idea of the working set. We'll also talk about the stride for programs that go through memory in regular ways. Most programs tend to execute the same small set of instructions over and over repeatedly. Typically, most instructions in the program are not used very often, but instead you have a few hotspots, and these are usually loop bodies. So the programs where execution is important typically execute a lot of instructions, otherwise their execution speed would be irrelevant. And those programs that execute a lot of instructions usually do that with loops, while loops and for loops and so on. And these loops tend to execute the same instructions over and over, and those are the instructions that are in the loop body. So here's an example, sort of short example of a program that has two nested loops, and the inner loop has a body with some statements in it, and those statements are executed over and over the most. So most of the time this program is executing the statements that are part of the loop body. And if you're a C programmer, you are familiar with this notation here. The loop test, the test for loop termination, and the increment of some loop index, those are also part of the loop body because those tests and those increments have to be executed each time the loop executes. So this is a hotspot for the program, and we would hope that this area executes quickly. But since it's a small thing, it typically will only execute a small number of instructions and probably only access a relatively small amount of data. So while this program is running, it'll spend a long time in this loop here. Okay, so for a long period of time, only the instructions here will be executed. Okay, while the program is in that section of its behavior, while it's executing that loop, it's executing only these instructions and nothing else. So these instructions are part of the working set for the program at that moment in time. After a while, the program will change, the loop will finish, and it'll go off and do some other stuff, so things will change. Okay, but the working set is something that's defined at a particular moment in time, and while the program is in this loop, its working set will include the instructions that are part of the loop. And then later on, the working set will shift over time as the program moves on to other areas and executes different instructions. I just talked about a working set in terms of instructions, where you have a small number of instructions that are executed over a long period of time, and other instructions are not really used. The same is true of data. Some variables are used often and a lot, and other variables are used very rarely. So at one particular moment in time, a program will tend to access a small number of variables a lot, and it will tend to ignore most of the other variables. So from a data perspective, not an instruction perspective, this variable sum is a hotspot because during this execution of the inner loop, this variable is both read and written, right? We're incrementing it, so we have to get the variable, and then we add something to it, and then we write the variable back. So this variable is in the working set when the program is in this loop. Of course, after a while, the program's behavior will shift, and it will move on to doing something else. As a result, the working set of data will also shift and change over time. The working set is a meaningful concept because most programs obey this principle of locality. This describes the behavior of many common programs. Now, there are some programs that are bizarre and weird, and they jump all over the place, and they do not exhibit the principle of locality. But by and large, programs, at least programs that are written by humans, exhibit this principle of locality. And what is that principle? Well, it says simply that if a byte of memory was used recently, it's likely that that byte will be used again in the near future. And if a byte of memory was used recently, then it's likely that nearby bytes are going to be used in the near future. So we can break these down into two different kinds of pieces and call one of them temporal locality, that is nearness in time, and the other is spatial locality, that is nearness in space. So if a byte of memory was used recently, it's likely to be used again soon. That's temporal locality. And if a byte of memory was used recently, then bytes with nearby addresses are likely to be needed again, and to be needed soon as well. And that's the principle of spatial locality. But these are both aspects of the more general principle of locality, and it applies to both data and instructions. Most programs exhibit locality both for their data usage and for their instruction fetching. Now we're ready to try and give a definition of the working set. We can say it's the set of bytes that were used recently, whether data or instruction, we don't care, but just the set of bytes that the program needed in the recent past. Another definition might be the set of bytes that will be needed soon in the near future, although we can't really know what the program's going to do, so it's kind of difficult to know what bytes are going to be needed. But generally, because of the principle of locality, these two sets are really quite similar, so there's a lot of overlap. So we can try to identify the sets that were of bytes that were used recently, keep those in memory with the assumption that the related bytes will be needed again soon. So the idea behind the working set is that if the working set can be kept in the cache where access is very fast, then the program will run faster. So the idea is we try to keep the set of bytes that were used recently in the cache as well as bytes that are nearby, and that way the set of bytes that we might need soon will be in the cache already. So when we bring bytes into the cache, we keep them. We try to keep the bytes as long as possible, of course, but the cache has limited memory, so occasionally we have to evict some bytes, but we prefer to keep the most recently used bytes in the cache. So when we bring in bytes to the cache, we also bring in nearby bytes, bytes that are close to those bytes that have similar addresses. That's because when we fetch, say, a byte of memory or a word of memory, we bring in a whole block of bytes. So when we fetch 1 or maybe 4 bytes, we end up bringing in 64 bytes into the cache, thereby loading in nearby bytes that might be needed in the future. A program's working set changes over time. So let's take a look at this program, and here's a timeline. At some point, we start the program executing, and it executes for a while until ultimately the program terminates. If we want to look at a section of the program's execution, we can look at a window of time, an interval of time. This might be 1 millisecond or whatever. We don't know. And we can ask which bytes were used during this window of time, and we can define that as the working set. If those bytes were all in the cache when they were needed, then the execution of the program was fast. There were no cache misses, everything was in the cache. And so our hope or our goal is to get the entire working set into the cache at all times. Of course, this is not achievable in entirety, but we can come close. So we want to try to get as much of the working set into the cache as possible. But as the program advances, the window moves, and so what's the working set in this area of the program's execution? Well, it's one set of bytes, but later on the program's doing something different and it needs another set of bytes. So the working set shifts over time. We can also ask about how big the window is. You know, how large is this window? We might measure it in terms of the number of instructions that are executed. Perhaps the instruction executes perhaps the program executes 1 billion instructions from beginning to end. Well, how big is the window size? Maybe it's 10,000 instructions, or maybe it's 1 million instructions, so it's a larger window. Obviously, if we look at a larger number of instructions, the working set is going to increase. The number of bytes accessed by 10,000 instructions will be smaller than the number of bytes accessed by 1 million instructions, most likely. Okay, you execute more of the code, you're going to touch more of the data, you're going to touch more instructions. So as you increase the window size, the working set gets larger. So the idea of the working set is more of a concept. It's not a rigorous, rigid definition. If you look at a larger window, you're going to see a larger working set. It would be nice to have larger caches to hold bigger working sets in memory, but you can't always hold as much as you want to in the cache. So you try to put as much into the cache as effectively as you can, given you have a fixed cache size. We can also look at what happens to the working set size as we look at more and more of the program. If you increase the window size all the way to include the entire program from beginning to end, then there's some maximum amount of bytes that program needs to access in order to run to completion. You know, maybe it executes all of its instructions. Maybe it touches all of its data. So there's some maximum. But as the window size gets smaller, it needs fewer and fewer of the bytes. And in the sort of the limit, when you're looking at just one instruction, well, you don't need very many bytes at all. You need the bytes that comprise that one instruction, maybe 3 or 4 bytes, and maybe that instruction touches a word of memory, so you need 4 bytes of data from memory. As the window size increases, the working set size also increases. So there's no magic point, no magic size for the working set, but we like large caches so we can get more of the working set into memory. The principle of spatial locality says that nearby bytes are likely to be accessed soon. And so let's look at an example of how this applies to data. Here's a little program that has a loop, and it does some stuff in the loop body, and among other things, it looks at an array. And it goes through this array, and you can see that it's going through this array sequentially. So since it touches every element of the array in turn, we say that it has stride 1. Okay, so it's going through the array, element by element. So how is this array stored in memory? Well, here on the left I show more schematically that the array is stored with one element directly after the next. So A0, A1, A2, A3, and so on. Now, each one of these elements may take several bytes, so perhaps this is an array of single precision floating point numbers. Each one of those takes 4 bytes. So here's another picture of memory showing the contents of this array. And here you see I've shown addresses for each memory location, as well as the byte that's in that memory location. And so here we have a group of 4 bytes. Here we have another group of 4 bytes. Here we have another group of 4 bytes. So the array is stored one element after the other. This program is going through the array element by element. Each element is 4 bytes long. So it's going to access this group of 4 bytes, and then this group of 4 bytes, and then this group of 4 bytes. But it's going, we say it has stride 1 because it's going through the memory in order and not skipping anything. Now let's look at this program, which is similar, but in this case we are incrementing the index by 4 instead of by 1. So we're going through the array by 4. In other words, we're accessing element 0, then 4, then 8, then 12, then 16. So we say that this program has a stride of 4. It's not so good. With a stride of 1, when we bring in this byte or these 4 bytes to access the first element, it's likely we'll bring in the nearby bytes for maybe elements 1 and 2 and maybe 3. And so we bring in bytes that are nearby, and since we're going through the program with stride 1 in this first program, we're going to have a lot more hits where the data that we want, it has already been loaded into the cache. In this program, we are jumping through memory, so we bring in nearby bytes, but we don't necessarily use those nearby bytes. And so consequently, this program is not going to perform as well, even though it may have the same number of iterations total. It's going through the memory with a stride of 4 rather than a stride of 1. So the second program has less data locality. The next item is consequently less likely to be in the cache, so we'll have a higher rate of cache misses and consequently poorer overall performance. Now let's take a look at a two-dimensional array. Here I've drawn the array the way you might visualize it. You can see it has 3 columns and it has 4 rows. And the array elements are 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and so on. How is this thing put into memory? Well, the programming language C and many other programming languages use what's called row major order. In other words, they store this row all contiguously in memory, followed by the next row, followed by the next row, followed by the next row. So here I've put this array in memory. In other words, I've taken this two-dimensional array and linearized it. And so we see that the first element A00 is stored, and after that comes element 01 and then 02. In other words, we store all of this row, which we can call row 0, and then we follow it by row 1 elements, so the 3 elements in row 1, and so on. So that's row major order. There's also something called column major order, which is to store all the columns one after the other. But most programming languages use row major order. So here's a piece of code that goes through this array. And it's a two-dimensional array, so the programmer has coded it as a doubly nested loop. So the inner loop, I've circled in red here. It accesses an array element, and the first loop iterates I. I is the row number, and the second one iterates J, the column number. So this thing goes through the array elements in this order: 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, and so on. So it's going through it in row major order. So it will access the data elements in this order: 0, 0, 0, 1, 0, 2. It does the first row. Okay, I is the row number. It does all of row 0. For I equals 0, it does all of the J's, 0, 1, and 2. And so it does all of the J's. And then it goes on increments I to the next row, and it does row number 1, and it increments j, 0, 1, and 2, and does all of row 1, and then it does row 2, and then row 3. So this program is well behaved. It goes through memory in order. It has a stride of 1, and it's going to have a lot of cache hits, and it's going to be well behaved. Here is a similar program. Okay, it touches the same array elements, but it just does them in a different order. You see that I have kept the I and j in the same order here, but I've reversed the loops. So this one will do all of j equals 0, and it will vary I more frequently. It will vary I more frequently. So when j is 0, it'll do I 0, 1, 2, and 3. So it goes through the array this way in a column order, and then it moves on to the next j, j1, and does 0, 1, 1, 1, 2, 1, 3, 1. And then it moves on to the last j, j equal 2, and does I0, I1, I2, and I3. So it's going through the array, all of the same array elements, just in a different order. So how does it do it? It goes through 0, 0 first, and then it goes to 1, 0, and then it goes to 2, 0, and then it goes to 3, 0, and then it comes back and goes to 0, 1. So it's jumping around a bit. Okay, so this one has a different stride. And since it goes from 0, 0 to 1, 0, we can say that it has a stride of 3. Now each of these may be 4 bytes or 8 bytes, so it might make more sense to talk about how many bytes it's skipping over. In this small example, it's possible that all of our data will fit into a single block and all be in cache from one load, so it may not make any difference. But where this really counts is when you have gigantic arrays with lots and lots of elements. Let's look at an example that's maybe more realistic. So we'll assume that our cache block size is 64 bytes. Each double precision floating point number is 8 bytes. So what this means is each cache block can hold 8 doubles. And let's imagine we've got just a really enormous array. And here I'm showing just a fragment of the array. Here's part of row 293, and here's the first part of row 294. Each one of these rectangles is supposed to be 8 bytes, so it can hold one double precision number. And since each block holds 8 doubles, the blocks are fairly small, like this. So let's imagine that we've got a nice, well-behaved program that has a stride 1 access. In other words, it's going through the memory in sequential order. So when it reads a double, so say when it moves from row 293 to row 294, it might read this double right here. When that occurs, that's going to cause this cache block, the entire block of all these 8 double precision numbers, to be loaded into this cache memory. So when the program tries to read one element from the array, it pulls in all 8, it pulls in 7 additional elements. And since it has a stride 1 behavior, it's going to then access those elements next, and those will already be in the cache now. So the first element will cause a cache miss because it's not in the cache, and we pull that block in, but the remaining 7 accesses will be cache hits. So we have 1 cache miss for every 7 cache hits. So we can define the cache hit ratio and the cache miss ratio as how many hits we have out of the total number of accesses. So in this case, just looking at what it's doing to the array, we see that it has a cache hit rate of 7 out of 8. Okay, that's about 87%, 87.5%. The cache miss rate, and unfortunately this thing misses 1 out of 8 times, or 12.5%. So you can see that this is a pretty good, well-behaved program.